All right, hello everyone. We're going to go ahead and get started. Welcome to our PTV Talk session for today. Today we will be showcasing some of the user presentations from our 2018 user group meetings. This is the first time joining us for PTV Talks. We began doing this series in April as a set of regularly scheduled web sessions where we can provide interesting content to our users. If you missed the previous sessions, you can always catch up by going to ptvtraffic.us and clicking on the Resources tab. There you will find the recordings of all the past sessions, and please continue to watch your inbox and the PTV America LinkedIn page to find out about upcoming events in the series. As I mentioned, for today we will be having two of our users who presented presentations at our 2018 user group meetings. Give them again today for a larger audience so that anyone who did not get a chance to see them at the UGM can have the opportunity to see them now. And for anyone who has never attended one of our user group meetings, you can get a feel for some of the things you may see if you attend our 2019 user group meeting in New Orleans on October 9th and 10th. We have two presentations today, one from Randy Johnson and a second from Joanne Arellano. We will be taking some questions today, so please feel free to ask any questions you may have in the questions box and go to webinar. We will answer as many questions as we can during the live webinar and then follow up with any additional questions after the fact. So with that, we will go ahead and get started. Up first today is going to be Randy Johnson. Randy, I'll make you presenter and you can go ahead and get started.
All right, thank you very much. Let's see, share my screen. All right, is everything showing okay there?
Yes, you're good.
Okay. All right, again, thank you for the opportunity to recap the presentation we did at the user group meeting last fall. My presentation is being a data detective to understand dynamic Vissim inputs. So this is a project we were working on for the City of Hillsboro and also jointly with the county. So Hillsboro is located west of Portland, Oregon. It's kind of in the heart of Silicon Valley where there's a lot of high-tech employment. There's also a lot of commuters, so you heading out of the area as well. So it's not just a one direction commute. There's traffic coming in and out both directions. So we're in a very highly congested area. And we have a light rail crossing through one of the major north-south arterials. And TriMet is going to be extending one of their rail lines further west, increasing the number of train crossings. So with that, our particular case study here is 185th Avenue. So it's a 5-lane arterial with ADT of a little over 32,000 today, and that's projected to increase quite a bit. And then we have an east-west arterial of just under 30,000 ADT, which is Baseline Road. So about 300 feet north of this arterial intersection, we have our light rail crossing, and we have a station just to the west here. So existing, we have 12 trains crossing. And with the red line extension, that number is going to go up to 16 here at year of opening, about 3 years out, and then in the years preceding, jump up to 19 crossings during the peak hour. So we already have congestion issues today, and 20 years ago when this light rail first went in, this was identified as an issue that the at-grade crossing is going to be a problem in the future, but there were no funds to do a grade-separated solution at that time. So we're now revisiting the grade-separated solutions of, do we grade-separate the road up and over? Do we grade-separate the rail up and over? Are there things that we could do to widen the intersection to provide additional capacity? There's little appetite in this region to go beyond 5-lane arterials, but we're looking at all potential solutions. And then we're also diving into any sort of rail or traffic signal solutions, anything we can do on the technology side to increase the efficiency of what we have. So that sort of sets the stage of our area. Oh, and one other unique aspect is when this was all constructed, the eastbound left was removed, and that traffic is accommodated through a jug handle movement here, just to minimize the conflicting movements and increase as much green time southbound as we can get. So the typical process for calibrating to a congested area with a rail crossing, we collect a lot of data. So we have our traffic counts. The peaking profile is extremely important. the train schedule and the speed of that train, the timing of the gates, the signal timing and the preemption sequence, and then a lot of field observations, a lot of queue length observations. And so as we go through this calibration process, it's getting the right saturation flow rate and doing any driver behavior adjustments to make that change. And then ultimately our calibration targets are the volume GEH, so making sure that our volume inputs and our volume throughput are matching, getting the queue lengths correct, both in duration and in time, and then travel time along the corridor. So that's just the general modeling process that we go through. The issue with this particular corridor is that while we have that typical PM congestion that happens on a daily basis, 2 to 4 times a week, we also get a super queue congestion. It's highly variable and increases that southbound queue from the rail crossing location, as shown right here. Increases it from about a quarter mile to a little more than 3/4 of a mile. So here's some drone footage looking southbound towards the rail crossing. You can see this queue spilling back. The drone pivots and looks north, and we can just see that queue extending all the way north, approaching the next major east-west street. So there's little redundancy in the connection here. So there's a lot of big arterials that are more than a mile spaced apart. So there's not that many parallel routes that traffic can jump to when it gets this congested. So we also looked at not just the vehicle impact, but we also wanted to see how this impacts the buses going up and down the corridor. So we looked at the Cad Avl Data, which is the onboard data collection system with on the buses. Basically tracks GPS and a bunch of other parameters. And so this is a sort of time-space diagram looking at the travel time reliability. So we're looking at the difference of the 90th to 10th percentile speeds. And when we get anything that sort of pops out here, that really shows where we have reliability issues. And we can definitely see this is roughly the rail crossing here, and going upstream to the left, and then we have our time of day on the vertical axis. And we can definitely see this sort of peaking curve of where we have some major reliability issues. And looking at the data, we could have up to 8-minute variability on this just over a mile stretch for the buses trying to get through here. So it's a major hit on TriMet's bus operations as well as the vehicle traffic. So our task was to figure out what causes this super queue condition, and then evaluate the build alternatives that have been proposed and see if that alleviates the issue or what other alternative solutions we can develop. So as part of that diagnosis phase, and we collected quite a bit of data, one of which was we installed cameras and recorded for several months of period at every signalized intersection upstream, so every couple hundred feet, and identified specific days where that super queue happened. So we could see the time of when it happened, the duration of when it happened, which then allowed us to look at the other data sets we were collecting, and we could go back and see exactly when and what caused these conditions. So the additional data sources that we looked at, we pulled the signal traffic controller logs through the preemption operations. We were able to see when each train arrived, the frequency, so are we getting closely spaced train events, and what are those crossing durations. So we have the rail crossing orders, which is basically the design of the gate operation, and that includes a time sequence of what should happen when a train goes through, but as we all know, there's all these variabilities. And so, yeah, I would say in a basic Vissim model, we might take that sort of planned crossing data and plug that into the simulation. In this case, we wanted to understand what the real conditions were. And then we also had GPS data from the train. That allowed us to look at what are the actual train speeds instead of the design speeds for the trains going across this crossing. So both the frequency and the duration of the crossing were incredibly important. So during the peak 2-hour period, we looked at in 10-minute bins, what was the frequency of train crossings. And we can see here that there are some outliers, especially in the 5 to 6 period, where we're squeezing 4 trains through in a 10-minute window. That's at the high end. So on these bars, the middle line is our median condition, and then our minimum and maximum. So there's quite a bit of variability in the bunching of trains through here. And then we looked at how long are these crossings. So I won't go too much in the details here, but I guess, and also to point out, one thing I do like about the PTV user group meetings is that you could get a little more technical with the presentation than you might do at a larger conference. So looking at these box and whisker plots here, we can see that the average is, right about 45 seconds for an average crossing event. But you can see these outliers, these 95th percentile crossings that are, pushing 2 minutes in time. And that's a lot of time to shut down a major arterial with that kind of volume. And we can see these long events that occur roughly longer than 2 minutes every 3 to 4 days. And that's pretty consistent with what we were seeing for the duration of the super queue events. So the next thing that we looked at was the train speed. How fast are the trains traveling in the area? And so we looked at the GPS breadcrumb data through here. We sort of extracted out the typical speeds, and we could able to see some hot spots where the trains are slowing down. Part of that might be there's a car stuck on the tracks, so the train's having to slow or wait for that crossing to be cleared. So this is just another factor that results in a longer crossing when the train has to go kind of lower than its typical or design speeds. So for the Vissim calibration, we really had to put in the train schedule, the train arrival time data at the stations, and the speed of the train. So this is where, instead of just having those average values, we actually had to put in the variability from the data that we collected. So that schedule reliability issue of the trains being bunched, putting in the arrival time distribution on that so that we do get those random arrivals in the simulation, to have a little bit more variability in the speed of the trains along the corridor. And then we were able to compare what we put into the model to the results in the field to calibrate these conditions. And so here's the comparison of the frequency of the rail crossings. So were we able to replicate the frequency between what was observed in the field and what we're producing out of the simulation? And we're able to get that pretty close. And we did the same thing on the durations. Now you'll notice on the model data, we don't have these really short crossings. And this was a bit puzzling for us at first because, well, there's no way a train can cross in less than about 35 to 40 seconds, unless it was going, double its speed. And so this is where we had to really dive into the rail controller log and basically found out that there were back-to-back events, and just the way the data was being logged triggered it as 2 independent short events. So that's where we really had to dive down and understand the data that we received from the logs and not just take it for face value there. So we were able to replicate those quite well between the model and the field data. We had a few events that spiked even higher in the simulation. We ended up running probably 50 different seeds, and then we were able to look at the individual runs to kind of create a collection of random seeds that really represented those super queue conditions. Additionally, we also have the field video data where we know exact conditions that of a super queue occurred in the field, and we also put in those exact model input parameters to replicate a particular day. This is sort of what I just mentioned. So again, we're having to really look at all of these variable conditions and making sure that we capture all of those in the simulation to represent two different scenarios. Again, the typical queue, that was 10 unique runs, basically with your sort of traditional model input parameters, and then looking at all the variations and distributions of input data, looking at a collection of isolated runs to identify the super queue conditions. Once that's identified, we're then able to test our build scenarios under those conditions. And so just another quick model comparison between the typical queue duration and then the super queue, how you get these big spikes in the duration. So here's a quick snapshot of the congestion plot. So these are generated using the relative delay parameter in Vissim using the link evaluation. It kind of gives you that Google Maps traffic effect of the conditions. And so we were able to produce these for every 15 minutes. And so we could see how that queue sort of builds during these events and then dissipates during the recovery post preemption. So conclusions here, when trying to simulate variable conditions, it's important to understand the factors that influence the congestion patterns. So it's often the distributions and variability in the data. There's a lot of analysis just on understanding the data and doing that diagnosis before you get into the actual modeling. Since we've done this presentation, we've finished doing all of our data collection. Our next step is to identify those short-term sort of technology solutions. And our next phase will be jumping into doing some software in the loop testing with controller upgrades on both the traffic and the rail side. So thank you very much. If there are any questions, I'm happy to answer.
All right, Randy, thank you very much. Yeah, if you have any questions, please go ahead and enter them now in the questions box and go to webinar. Did have one come through here asking for a little bit more explanation about how you identified the random seeds for the super queues.
So with that, we run each of the 50 runs, and then there's a few key parameters that we looked at. One is the vehicle travel time was probably one of the primary indicators, but checking that any latent demand. We don't want to choose a run that's just completely blowing out the simulation if due to the random variation of the distributions, if we end up with, you know, a triple back-to-back event that we really don't see in the field. So really it's identifying that spread of the distribution on the travel time, and then there's sort of that threshold of, all right, once it gets above 7 minutes or so, you know it's going to be in that super queue condition.
Okay. Also, so for each run, were you using the exact train schedule, or are you just relying on the Vissim distribution that you entered over the course of time?
So we put in the exact trains. Well, there's two different scenarios we're in. One is we put in the exact train schedule, and then we have the actual arrival data that we use to develop basically a time offset or schedule variation distribution. But we also put in exact schedules of the arrival to simulate specific days, so we can analyze how do these solutions work for a particular day that was observed.
Okay. And was there any consideration given to modifying or optimizing the train schedule in order to prevent these types of super queues?
Most of the back-to-back issues are related to westbound trains, which this is nearing the end of the line. And so these trains are interlined all the way through the far east side of Portland, and there are some other major system bottlenecks. Trying to some other projects that are trying to reduce those, but there's so many points in which the trains can get hung up along the way that it's difficult to schedule them by the time they get to this end. Eastbound trains, this is near the start of the line, so eastbound trains are fairly on schedule. Some of the technology solutions we're looking at are how we could control an eastbound train arrival across the crossing here relative to when a westbound train arrives.
Okay. Very good. Randy, thank you very much. I think with that, we'll conclude the live questions. If there's any other questions, we can follow up a little bit later. So thank you very much, and we'll go ahead and move on to Joanne's presentation.
All right, thank you for the opportunity.
Yep, thank you. All right, so next presentation is Joanne Arellano from JMT. Unfortunately, she is unable to be here today, but she was kind enough to go ahead and pre-record her presentation. So we're going to cue that up right now. And she did mention that if there's any questions during the course of her presentation, she would be happy to follow up later. So as any questions come to mind, please feel free to go ahead and ask them, and we will follow up with you later.
So good afternoon, everyone. I'm Joanne Arellano from JMT, and I'm here today to present a very unique and award-winning project. First, I just want to thank PTV for giving me the opportunity to present this project at the North American UGM back in October. And I'm very grateful that they have asked us to present this again for all of you today. So the project that we'll be talking about was a project done with the DRBA, who is the Delaware River and Bay Authority. They're responsible for providing transportation links between New Jersey and Delaware, and they're responsible for operating ferries, regional airports, as well as the Delaware Memorial Bridge, which, if any of you have driven from Washington, D.C. to New York City, and you've driven there using the New Jersey Turnpike, you most likely have driven along this bridge, and that's what this presentation is about. So what makes this project unique is that we created monthly Vissim models for one calendar year, and it was created for each month, and it was comprised of 3 peak periods, which results in 36 Vissim models. So I'm going to talk to you exactly about why we did that and the methodology involved. Let me go in more detail about exactly what the presentation will be about. So like I said, I'm going to give a background about the project, go over the methodology, also discuss some challenges that we encountered and the lessons that we learned from it. But I'll also go over an additional analysis that DRBA asked us to do on top of those 36 models. And then I'll go over some other applications where creating monthly Vissim models for a full year might be helpful. So for the limits of the study area, it actually started on the Delaware side at the US 13 interchange. It extends across I-295 and ends on the New Jersey side at the Route 130 interchange. Within this study area, I-295 is comprised of 4 lanes in each direction roadway. And along this segment is the Delaware Memorial Bridge. Just south of the bridge, along the southbound side, is also a toll plaza. And within this study area, there are also 5 signalized intersections. The peak hours that we analyzed was the weekday AM and PM, as well as the weekend. And the months that we analyzed was July 2015 to June 2016. So the whole purpose of the project, because some of you may be wondering why that many models were created, was so that DRBA could have monthly Vissim models to represent baseline conditions, typical conditions when there are absolutely no lane closures. So they wanted these models so that they could be able to identify during times of the year exactly, what specific peak hours during a specific month that their study area might have some capacity constraints. So here's a picture of one of the level of service tables that we created for the report that summarized all of the analysis results from these models. And as you can see here, in August on a weekend, the southbound 295 operates with a level of service E, which was no surprise to us because level of service E in this area, especially during the summer, is actually quite expected. You see, with the Delaware Memorial Bridge, it is quite used very heavily during the summer because if you're traveling from the south and going towards the New Jersey shore, most travelers use this bridge. And the same thing in the other direction. If you're coming from the north and going to travel, just do a weekend trip to the Delaware or Maryland beaches, then you most likely traveled along this corridor. So the level of service E on an August weekend was not surprising to us at all. So the point of these baseline models was then DRBA can now take those models and see what the impacts would be if they closed a lane. For example, let's say that the DRBA had to do some maintenance work on the Delaware Memorial Bridge. Well, if they wanted to do that work, they're thinking about doing it in June, they could take the June model and remove one of the lanes because they would need a lane closure, and then they could see what the impacts would be to the traveling public if they did that on a peak hour in June. So that was the point of the models. So in order to create all these models, we had to collect various volumes at various locations throughout the study corridor. And they were done at various stages throughout the project. So we did one-time volume collection at the 4 signalized intersections. Then we did seasonally, we collected volumes at all of the on and off ramps at the 3 interchanges within the study area. And then monthly, we collected volume data along the southbound side at the toll plaza and also along the northbound side just adjacent to the toll plaza. In addition to volume data, we also had to do observations along the corridor so that our models would replicate what we saw in the field. So we collected one time on and off ramp merge and diverge interactions at the interchanges. And then seasonally, we observed the toll plaza to see, okay, at the toll plaza, how many vehicles were using the easy pass only lanes, and how many vehicles were using the cash lanes. Also, we noted of those vehicles, how many were trucks and how many were passenger cars. And then monthly, we observed the signal operations at the signalized intersections. Also took travel time runs along the corridor. So here's just a picture of one of the field sheets that we used during those travel time runs. We also collected spot speed data at various points along the study corridor. Additionally, we observed monthly the toll plaza queues, as well as the number of lanes. So for a number of lanes, we wanted to see how many of those lanes were easy pass and how many were cash. And in regards to toll plaza, we wanted to see in each of those lanes, how long were those queue lengths. So why Vissim? Because someone might think, you know, when they think about creating Vissim, and especially 36 models in Vissim, that's probably a question some would ask. Why exactly did you want to use it? And the main reason was just because of all the unique characteristics of the study area. So we had to model lane drops with all the interchanges, all of the merging, diverging areas. They were closely spaced weavings. And then we had a toll plaza. So there were a lot of very unique situations in our study area, and we knew Vissim would be the best choice to model those because of all the adjustments that we can do with the driver parameters. As far as calibration, we decided to calibrate our models looking at travel time, spot speed, and volume. We used the FHWA toolbox as a guidebook to help us determine, you know, what's the threshold? How much percentage should our Vissim results be with our field results? And what we found was that, you know, we wanted the results to be within 10%. So we wanted the Vissim results to be within 10% of the field results. And we made sure all of the 36 models we created that was the case. So some of the challenges that we encountered was at one of the interchanges, which is actually at the southernmost point of our model, at the US 13 interchange, there was construction happening. And one of the ramps, which is shown here in the yellow box, the ramp from US 13 to southbound I-295 was under construction. And that geometry of the actual ramps is going to be modified. As shown here in red on the top of the page, you'll see that a new ramp is being constructed now to accommodate those movements that want to access southbound 295 from northbound Route 13. So with that model geometry change, we had to update our models to account for this new interchange layout. Another challenge that we encountered was collecting data when there were lane closures along the bridge. So the point of our models was to create baseline typical conditions where there were no lane closures. But it's hard to collect, field data when there's actually a lane closure in place due to construction or maintenance. But we found one workaround, which was to collect, for example, if we wanted to collect travel times, we found that if we collected the travel times a little outside of the peak period, because we knew that if all the lanes were open, the traffic conditions would be more free-flowing. So if we collected the travel times during that time, that it would represent the peak period better. So that is exactly what we did. The DRBA asked us to do an additional analysis. What happened was during summer Saturday, the DRBA had to do maintenance along the Delaware Memorial Bridge, so they actually closed the lane. But when they closed the lane, it actually had a 5 to 8 mile backup. On the southbound side, that backup actually extended all the way to the New Jersey Turnpike. But when you see volumes that's shown here on this diagram, about 4,900 vehicles, those typically, that demand could be accommodated in 3 lanes of traffic. But on this particular summer Saturday, when they did have 3 lanes open and this much demand, they had extensive backups. So the DRBA asked us to create a model replicating this. So we did one model where we took one of our summer models and we removed the travel lane. And when we ran the model, it still had free-flowing 3 lanes. We didn't see the backups that DRBA saw that day. So we did a second model where now we added some desired speed decisions. With those speed decisions, it did reduce the speed of the drivers in the work zone, but it didn't generate that backup that they saw that day. So we did some research to see, what can be done. And we came across this Missouri DOT report that was put together that talked about calibrating analyses in work zones. And when we reviewed the document, we found that there were some parameters in there that talked about adjustments to do for driving behaviors. So we looked at the ranges that they had in that guidebook, and we applied it to our models. So we created a third model with those, with the reduced travel lane and the desired speed decisions, but also implemented the driver behaviors, some adjustments. We extended the runtime of the simulation to 2 hours. And then we saw the desired backup. So we saw the 5 to 8 mile backups that DRBA saw on that day. So the good thing about creating this model for DRBA is now, let's say that they wanted to do that lane closure in June. Well, they can take that June baseline model that we created, and they can remove a lane, but now they can also take those driver behaviors that we determined in that 5 to 8 mile backup model and take those driver behaviors and apply it to this June model that they want to see what would happen. So now they can have a good idea of what may happen if they do close a lane. So some of the lessons we learned as part of this project, I did already talk about the field data and how we found a workaround to collect it in the work zone. But another lesson we learned in regards to collecting data was travel time runs and how beneficial it would be to collect travel time runs in multiple lanes at the same time. Because this particular area has multiple lanes, each lane kind of operated differently. So if we are able to collect, travel time runs in more than one lane at the same time, that would have been very helpful. Also learned about the attributes of a work zone, like how work zones impacted drivers. And then also for driver behaviors, we saw that this study area was very directional in regards to driver behaviors. So if a driver was coming from the New Jersey side and entering Delaware, and vice versa, if there was a driver coming from Delaware and entering New Jersey, they each drove very differently. So we actually implemented different driver behaviors for each side. But one of the reasons is that when you're on the Delaware side, when you're coming from the south driving north, there's much more interchanges and lane drops and more interactions and more characteristics of the roadway that would have a driver drive differently there. Another lesson we learned was how to model a toll booth, and also the impacts of grades that they had on the models. So some other applications where this may be useful, where perhaps reviewing monthly models in a calendar year would be helpful, would be, let's say you have a corridor that is comprised of a shopping center that peaks during the holiday months. So it may be useful to know, okay, how does this corridor operate during typical, conditions? And then knowing, okay, when we have these certain times of the year, when we have much more demand, much more trips coming to the shopping center, how does the corridor operate during those months? And maybe it might be helpful for planning purposes to kind of help come up with some solutions to how to handle those traffic during those particular peak times of the year. And the same thing can apply for event planning. If you have stadiums that peak during certain times of the year, maybe only during football seasons in the fall, where you'll really see the corridor operating, at capacity at times. So it's just very helpful, maybe helpful to see what traffic conditions would be like, and looking at it at a monthly, throughout a year kind of overview. So that's it for my presentation. But I want to again thank everyone for joining today and listening in. And if you have any additional questions, feel free to email me. And that's it. Take care.
All right. Thanks very much to Joanne for taking the time to record that presentation for us today. As I mentioned earlier, she's not here live on the call today, so she said she was more than happy to field questions later and get back to everybody who had questions. So please feel free to go ahead and enter your questions, and we'll pass those on over to her. As you're asking any questions you may have, we'll begin to wrap up with just a couple of reminders. There will be a recording of today's session. You will receive a link tomorrow in the follow-up email. And as always, for this and all the previous recordings, you can find them at ptvtraffic.us under the Resources tab. Our next session is going to be on Thursday, June 13th, again at noon Eastern Time. So please watch your inboxes and the PTV America LinkedIn page for more details about that session and for a link to sign up. And as we talked about, this was some presentations that were originally done at our 2018 user group meetings, So please mark your calendars for our 2019 user group meetings, which will be October 9th and 10th in New Orleans. This will be the 40th year for PTV as a company, and it will be our 20th annual user group meeting here in North America. So please join us for the celebration. Thank you everyone for attending. We'll keep it open just a few more minutes so everybody has a chance to ask their questions. Hope you have a great rest of your day, and for everyone here in the U.S., please have a safe and relaxing Memorial Day weekend. Thank you.